So thank you all for joining this final Applied PD seminar of our academic year here at the University of Washington. In case you're wondering why we're still going with our academic year here at the University of Washington, we are on quarters, not semesters, so hence this kind of late final seminar. Our speaker today is Annalisa Calini from the College of Charleston. Annalisa got her PhD at University of Arizona under the direction of Annalisa Calini, I believe.
Yes.
And after a couple of postdoctoral stints at the Australian National University and Case Western, and also briefly MSRI, she's been at the College of Charleston since, kind of interrupted with different stints as a program director at NSF. And today she's going to tell us about Soliton equations and geometric flows. Thank you, Annalisa.
All right, so thank you, Bernard, and thank you, Jorge, and the organizers for inviting me. So this is not going to be a really applied talk, but think of the application of PDEs to geometry, in particular geometric flows. Okay, so I will hope that you, by the end of this talk, you take home a few key points. There will be some technicalities, and so if you want to interrupt me while I'm talking, please do. I welcome questions. So roughly the way I will structure the talk is showing the role of moving frames and integrability in so-called geometric flows, starting with the famous applied PD in some sense, which is the vortex filament equation that models a very simple, simplified dynamics of vortex filaments in ideal fluids. I'll then show you where the KdV comes from in the geometric context, and then I'll talk a little bit about discrete settings. So I'll leave the realm of PDEs, but the methods will be very similar, and show you that sometimes the geometric context provides more insight than the actual PDEs. So here are the take-home points that I briefly anticipated. So first of all, what is a geometric flow? So a geometric flow is the evolution of a geometric object. Think of a curve. In this talk, we'll only talk about curves or a surface in a certain manifold, and a flow that is invariant under a group of symmetry of that manifold. The canonical one would be, for example, the motion of a curve in Euclidean space, invariant under the Euclidean group. Now, one thing I want to point out is the definition of integrability of a geometric flow. So we will say that the geometric evolution equation is integrable if the PDE that describes the related evolution of the invariants such as curvature, torsion, and so on, is an integrable PDE. So it's really, in a sense, an indirect definition of integrability. Now, again, the famous case is the binormal flow or vortex filament equation. It's closely related to the nonlinear Schrödinger equation, and what the NLS potential encodes here is the curvature and the torsion of the evolving curve. And I will get into this a little later. So in this sense, we say that the vortex filament equation is an integrable geometric flows because the associated PDE for the invariants, the geometric invariants, is an integrable one. Now, another major key point of this talk is the role of invariant moving frames. We'll see a famous one very soon, the frenetic frame, and it plays a key role in the integrability of the geometric flow, together very often with the preservation of the lowest order geometric invariant, for example, arc length. And finally, as I said before, the geometric framework and the geometric picture sometimes actually is clearer and in a sense cleaner than the picture at the evolution of the invariants. And I will give you an example toward the end of the talk, where the integrability of the system is actually revealed in this geometric flow setting rather than at the level of the geometric invariants. So let me start with the example of curves in tree space. So I'm sure at some point in your career, you have seen the frenetic equation for curve theories called curves in tree space. So this is a triple of ODEs for the unit tangent vector to a curve, the normal, and complete the triple with as a right-handed orthonormal triple, you get the binormal vector. Now, it's an adaptive frame in the sense that as you slide the frame along the curve, the frame solves this triple of ODEs that tells us how the frame moves as I slide along the curve. The geometric invariants here are, well, arc length, which I expressed this equation with respect to, the curvature kappa, and the torsion tau. And they describe really the shape of the curve. Now, this is not the only frame. There is a nice paper by Bishop way back in '75, which is called There is More Than One Way to Frame a Curve. Well, if you think of the normal vectors, the N and B, the normal and binormal, which are in the normal plane to the curve, and you just rotate them, well, you simply create a different orthonormal frame. This kind of frame can be chosen so that they satisfy these new Frenet-like equations. They are called natural Frenet systems. And in particular, notice that we are looking, in this case, at so-called frames of constant rotations. In particular, frames of least rotation, where this constant sigma is 0, they're called parallel frame because as the normal vectors U1 and U2 evolve by sliding along the curve, their velocity is parallel to the tangent of the curve. If I switch to such a natural frame, and I by the way, this natural frame is related to the Frenet frame in this way. I wrote it in a complex form, but essentially the first expression here describes simply the rotation of the N and B vectors in the normal plane to the curve. These new invariants, kappa 1 and kappa 2, by the way, are called the natural curvatures. And they are related to the kappa and torsion in this kind of interesting way. So the complex modulus here is the curvature kappa, and the phase is the antiderivative of the torsion, possibly modified by your constant rotation parameter. Now, a way to interpret what we are doing here is to change from R3 with the usual inner product to the space of skew-Hermitian matrices, so the algebra SU2. There is a natural correspondence that sends a basis of R3 to the Pauli matrices, and every vector in R3 to a skew-Hermitian matrix. Again, the dot product here becomes the natural say minus a half times the trace of the product of the matrices. Now, because S2 as a transitive action on orthonormal frame, or equivalent, think of the following. Every orthonormal frame can be rotated to a standard frame. Then there will exist an element of the group that conjugates my basis frame to the natural frame. I can insert this expression here. Let's see if I can go back. Into the natural frenetic systems. And this is going to give me the way this conjugating matrix in the group changes as I slide along the curve. If I introduce a complex quantity Q, which is simply this combination of the natural curvature, factor over half is there for convenience in some sense and for comparison. And I rename my rotation parameter as 2 times lambda. I think almost everyone in this audience is going to recognize the system that I get for the group element omega. And this is nothing but the AKNS system, which is the spectral problem of the nonlinear Schrödinger equation and various other equations. So if you don't know this system, this is named after Ablowitz, Kauper, Newell, and Sigur, who wrote it down when studying and uncovering the integrability of the NLS equation. Okay, so in a nutshell, what are we doing here? We have constructed a moving frame that essentially gives you the encoding of a famous spectral problem of an integrable PDE. And this AKNS system, conversely, can be interpreted pretty much as the natural frame system for a curve in Euclidean space. So there is the geometric connection. Now, how do you get integrable flows? Well, you get integrable flows by adjoining a compatible evolution. So your omega, which is now your moving frame, is now depending also on a temporal variable t. You assume that a temporal evolution where this script V is a 2 by 2 matrix that belongs to the Lie algebra SU2. By the way, this condition that we stay in the Lie algebra, it's a pretty key in integrability, and it corresponds to a preservation of arc length of the curve. And when we look at these two systems, we want them, number one, to be compatible. So we want to have a common solution. So in other words, mixed partial commute, if you wish. But also we want the compatibility condition or zero curvature condition to be independent of parameter lambda, which is the spectral parameter in your AKNS system. Now, when you do that, you're going to get an evolution for the Q, which encodes the curvature and the torsion, and you can construct integrable evolutions. And here is the example. If I adjoin this evolution of the frame, which again, you will recognize this as the temporal part of the AKNS system for the focusing NLS equation, you're going to come up with this famous PDE. For the complex curvature, I would call it. Remember, your Q is encoding the curvature of the curve and the torsion of the curve. So evolution of the frame corresponds to an evolution of the curve itself. And this is a famous flow, the binormal flow, or vortex filament equation. And here is in blue, it's expressed in terms of the natural frame and the natural curvatures. And as a bonus from all of these geometric comparisons, we get the Hashimoto map or Hashimoto transformation, which takes a curves in space evolving by the VFE and gives you a complex potential evolving by the focusing NLS equation. All right. Now, this is a bit of a quick slide, really, to show you that now
Annalisa,
we have...
can I ask you a question?
Yes, Bernard.
On the previous slide,
Yes.
so you have the Hashimoto map, which takes a solution of VFE and I guess you solution of focusing NLS. How about the other way?
Yes, the other way, by the way, so let me say something here. So your frame will be the triple T U1, U2, for example. And there is a way from the Frenet equations, in the way I rewrote them here, this is the equivalent of Frenet equation written in, let's say, in the SU2 context. There is a way to reconstruct a curve from a fundamental solution matrix of this system. I skipped this part because it would take me a little bit of time. But given a fundamental solution matrix of the system, you can actually reconstruct an evolving curve in your Lie algebra. Essentially, what you do is you differentiate omega with respect to the spectral parameter. You pull it back to the identity, obtaining an element of the Lie algebra for lambda real, and that will be a curve in R3 after the correspondence between skew symmetry matrices and Euclidean space. And so, you can show that the curve will evolve by the vortex filament flow. Yes.
So how about the boundary conditions?
The boundary condition, yes. If you start, for example, with a periodic potential of NLS and you want to reconstruct a periodic curve, that doesn't work all the time, but for large classes like n-phase solution, final gap solutions, there are closure conditions that are actually very delicate. And so let me not get into that because it would be a whole other talk. But yes, you can essentially go back and forth, provided some technicality. And you can maintain boundary conditions, whether they are linear asymptotics or periodic or quasi-periodic for large classes of solutions.
Okay, thank you.
Yes.
Can I just throw in one tiny comment for Bernard?
Yes.
And of course, Annalisa knows this super well, which is that, Bernard, if you look at NLS with Qs which decay rapidly at infinity, it will correspond to curves which are asymptotic to straight lines.
Right.
And then you could, so that is the easiest case where you can go back and forth between the two.
But it gets more complicated if you're interested in closed curves and then have to worry about, I mean, a typical solution of a typical finite genus solution of NLS will not be periodic. It will be quasi-periodic, and then, you know.
So you'll have to, so if you take a typical solution of NLS, that's correct, quasi-periodic, you can actually associate to it a periodic curve. You make use of Galilean type of transformation, and that reconstruction formula I really skipped pretty much.
Okay,
but
thank you.
Yes.
I don't want to take more time away from your talk. Thank you.
So this slide is here because you have correspondence now between the VFE and NLS, and you have some remarkable geometric correspondence. This work goes back to actually Ron and Joel Langer, Ron Perline and Joel Langer. who studied in depth the bi-Hamiltonian structure of the vortex filament equation, the connection with the bi-Hamiltonian structure of the NLS. So both of them can be written in two different ways as Hamiltonian systems with respect to two Hamiltonian structures, what I call J and K and J tilde and K tilde. And notice that on this side, the structure, and in a sense, much simpler. One is essentially a rotation by 90 degrees in the normal plane to the curve, and the other one is essentially differentiation with respect to arc length and conjugated by this rotation. They both have, of course, recursion operators. The two Hamiltonian structures are compatible in the sense that the corresponding Poisson brackets give rise to a pencil of Poisson brackets. And once you have that, you can write down recursion operators. The VFE is very remarkable in this context because it has a geometric recursion operator. And that's the tangent vector cross product with the derivative with respect to arc length. Here I show you one of the two Poisson structures, the one corresponding to J for VFE, and that's the so-called Marsden-Weinstein Poisson structure. Now, if you invert one structure and combine with the other, you're getting a recursion operator that allows you to construct a hierarchy of vector fields and a hierarchy of conserved densities. And that's really where integrability comes from. Now, with the Langer and Perline, they went in depth into the analysis of the Azimuth map. They computed their differentials. It turned out to have a fairly beautiful expression in terms of the two Poisson structure of the NLS equation. And that allowed them to essentially found an equivalence at the Poisson level between the VFE and the NLS, which can be summarized by saying that the Azimuth map is a Poisson map that maps the Marsden-Weinstein Poisson structure for vortex filament that came quite a few years before the paper by Ron and Joel to the fourth Poisson structure for the NLS equation. So there is a shift in structure, but that shows the deep equivalence of the two equations. And by the way, these created a sort of saying that the NLS equation is a Euclidean, or the VFE is a Euclidean a Euclidean representation, in a sense, of the NLS equation or realization. All right, you probably are asking, what if you look at a simpler PDE, what about the KdV equation? Where does it arise in the context of geometric flows? Well, it arises as a flow on curves in the plane, but the group of symmetries now changes. So remember, we have evolution of curves in R3 subject to the Euclidean group. And now we have evolutions of curves in R2, but now this is going to be a curve evolution, which is invariant under projective transformation. In this case, linear fractional transformations. So a little bit of a definition of the setting. The type of smooth curves that we consider are so-called star-shaped. This notation here stands for the determinant of matrix whose first column is the position vector of your gamma, and the second column is the velocity of your gamma, the first derivative. So a curve is called star-shaped whenever these two vectors are never parallel. So the determinant is never equal to 0. And because I'm talking about determinants are invariant under the action of the spatial linear group. And that will be the underlying symmetry group of these curves. If I reparameterize this curve, in such a way that, for example, gamma sub s, the determinant is equal to 1, I will say that this curve is parameterized by centroaffine arc length. So this geometry is called centroaffine geometry. Now take a look at this condition for arc length parameterization. If I differentiate it with respect to our length parameter, assume and impose that the arc length is constant, this gives rise to a geometric invariant because the acceleration now has to be parallel to gamma. So it will be some multiple, and p is a function of s times gamma. This p, which is itself expressible as a determinant, is called the centroaffine curvature. So in centroaffine planar geometry occurs, the differential invariants turn out to be the speed, the centroaffine speed, and the centroaffine curvature. Now in the mid-90s, again, Pinkall looked at this setup, and he looked at the space of arc length parameterized curves in centroaffine, in the centroaffine plane, up to translation. So we can call unparameterized star-shaped curves. And he found that a very simple two form, this is simply the area form, provides a symplectic structure for this space. Now, every time you have a symplectic structure, you establish a correspondence between smooth functionals, and these would be Hamiltonians, and Hamiltonian vector fields. In this case, the vector fields we're interested in are vector fields that preserve arc length. So they will be generically a linear combination of your curve and the first derivative. That's all you have in terms of the germs of your curve. They will determine the invariant. This condition, -1/2 beta s for a generic beta, ensures our length preservation. And the correspondence given by this symplectic structure provides you Hamiltonian arc length preserving vector fields given a Hamiltonian functional. And if you take as Hamiltonian the total curvature, the total centroaffine curvature, which by the way is actually 2 times the area swept by the tangent, you're going to get Pinkall's flow. Is very simple. Is the vector field is this linear combination of gamma sub s and gamma with this coefficient determined by the curvature and its derivative. But when you work out the corresponding evolution for p, for the curvature, that's KdV. So the KdV arises naturally in this setting. How are moving frame coming in explaining integrability? So if you think of the VFE case, by the way, all we did is we said, okay, let's construct an adaptive frame. In general, a moving frame is a slight generalization of it. You can think of having a curve and lifting the curve up into the so-called frame bundle. And the frame bundle here is actually the group of symmetry. So a moving frame is an equivariant lift of the curve into the group of symmetry of your manifold where the curve lives. Equivariant means that if you act on the curve by your group of symmetries, correspondingly, you are acting on the moving frame. In the same way that if you rotate the curve, the frenetic frame in R3 rotates with the curve. In a series of papers by Fels and Olver, a procedure for constructing moving frame, it was an algorithm in some sense for constructing moving frame was given. And the key, a key point of their paper was a normalization process. So essentially you normalize you write down normalization conditions that will allow you to introduce, in some sense, some parameter that will play a role of the spectral parameter of integrability. So in a nutshell, you construct a moving frame, you normalize it, and for example, given this normalization, what you see here is a right or left normalized simply means with respect to the right or left action of the group. So if you are constructing a right frame, you can get a left frame simply by looking at the inverse of this matrix. This construction gives you this frame. Notice this frame is kind of different from what we saw for the VFE. The curve is part of the frame. And of course, the velocity modified in this way by a multiple of the curve is the second vector in this frame. Remember, you are in R2, so now you have 2x2 matrix. Do the same as you do for Frenet systems. Differentiate along the curve, pull it back, right, to the Lie algebra. And what you are going to get is a matrix that encodes the differential invariance. If you remember, for NLS, we had a Lie algebra matrix encoding the potential Q, which contains the geometric invariance, or think of the Frenet system that's expressible in terms of kappa and tau. And in this case, what we read off here is we are in Arlem parametrized curve, so we only see the P. But in these guys here, this will contain also the velocity vector, the velocity, the Arlem parameter. Again, same game. Adjoin a compatible evolution. If rho, your moving frame, evolves by this, we require incompatibility of these two equations for all lambdas, is going to give you the KdV equation. So that's a first step of obtaining the lax pair, in some sense, for the KdV equation encoded in the moving frame of your curve. Now, I need this for later, but this is part of a far larger picture. What turns out to be is when you look at the Lie algebra of the group, and you go to the loop algebras, these are maps, smooth maps from the circle into, let's say, the Lie algebra SL2. The dual of this loop algebra has two natural Poisson structures. They were found by Drinfeld and Sokolov, and they are fairly general structures that enter in KdV-like systems. And the key observation we made quite a few years ago with Tom Ivey and Gloria, Marí-Beffa, is that these Poisson structures reduce to suitable quotients to give the bi-Hamiltonian structure on the space of differential invariance of curve parametrized by centroaffine arc length. So we can recover KdV, but we can also recover through the moving frames the integrable evolutions like Pinkall flows and flows in that hierarchy. So the way it works in a nutshell, and just, I know this is a little technical, but what we do really is we look at a moving frame. Now there it is, a lambda equal to 0. I did not choose arc length, so now the centroaffine speed is coming in. And once you look at the matrix of invariance, what is known in geometry as Maurer-Cartan matrix, that can be identified as an element of a certain quotient of the loop algebra by a normal subgroup through a certain gauge action of your group. Once you have identified this, you can reduce the Drinfeld-Sokolov general Poisson brackets to this quotient, and what turns out to be is exactly the two Poisson brackets for the KdV equation, and some of you will recognize it. If you take a b equal to 1, you get the third derivative here coming up. This is in the second, in the what I call the zero Poisson bracket, the simplest, you get the derivative, and this coincide completely with the two with the bi-Hamiltonian pair for the KdV equation. Again, you will ask, is there an Asimov map for this kind of flows? Yes, there is, and that's simply the sort of centroaffine curvature. So you can go from your gamma to the curvature P. You can compute its differential. You get a very clean expression in terms of the second Poisson operator of the KdV hierarchy. And let me kind of skip this. This is just to tell you that you can construct a recursion formula. It's not as nice as for VFE. You don't get a recursion operator for vector fields that look geometric, but you do get a recursion scheme for densities, for the Hamiltonian density. And at the end of the day, you get a similar result as the one of Langer and Perline. And the statement is simply that if you look at every flow, each flow of the KdV hierarchy, that can be interpreted as the evolution for the curvature of a curve evolving by a geometric flow in centroaffine R2. Moreover, that equivalent of the Asimov map, taking your curve to its centroaffine curvature, is also a Poisson map that takes the Pinkall area form to the second Poisson structure of KdV. Again, there is a shift in Poisson structure, but this shows the equivalencies of the two systems of PDEs, the geometric flow in centroaffine R2 and the KdV equation.
Annalisa, very
Yes.
quickly. So maybe you just said this, but I'm not sure I heard correctly. If you look at the higher order geometric flows, are they local? That is to say, are the coefficients?
Yes. They're all local. They're all local flows. The coefficients of the vector fields are functions of the curvature and its derivatives. Yes, they're all local. In fact, you know, the same game can be played with the centroaffine evolutions in R3. And what's very interesting is that the corresponding integrable PDEs coming out there is the Boussinesq system, a double hierarchy, and again we get local flows with the same kind of approach through moving frames. All right. Oh, by the way, if you are interested just in seeing how do these curves move in centroaffine space, and so we have a couple of examples here that Tom Ivey computed. These are quasi-periodic solutions. In fact, they are periodic curves coming from finite gap solutions of the KdV equation. And so I guess what you notice here are 3 time frames. So I think it's from dark to light. So the dark curve is the initial condition. The intermediate is at intermediate time, and then the lighter is at the final time in some sense. So this curve kind of slide on itself, oscillate. It's not a rigid motion, as you can see from the track of a point on the curve, which is on the right. Just one second. Can I extend the scheme to negative order flow? Well, we did a couple of examples, but we didn't really extend it to all of them. I suspect you can. Yes, I suspect you can using the recursion scheme.
Thank you. That's basically for the negative flow of a KdV hierarchy, not a positive direction.
Right. I think you can, but we haven't really looked into it except for a couple of ad hoc examples.
Okay.
Yeah.
I will ask you later. Thank you.
Yeah. Thank you.
Mm-hmm.
And by the way, okay, let me see. Here is genus 3 again, just to show you, notice that this curve, I think you can convince yourself, the velocity vector to the curve, the tangent vector, is never parallel to the position vector. In that sense, they're called star-shaped. They resemble, star-shaped domains in complex analysis. All right, discrete setting. This is, in a sense, a work I took up with Gloria, who got interested to discretizations of the KdV equation and the related Poisson structures. And this is the example where the geometric picture actually leads to some nice results. So let me give you an example of what I mean by this discretization. It's not a full discretization, it's a discretization in space, but the time is still continuous. So I'm leaving the realm of PDEs. And as you know, integrable PDEs are delicate, right? You perturb a PDE, it loses integrability. So the business of attempting to come up with integrable discretizations of integrable PDE is a tricky one. And here is a simple model. It's called the Volterra model. It's considered to be a discretization of the KdV equation. It's not straightforward to show it, but it has also a geometric interpretation in terms of polygons on the projective lines. So you can think of a sequence of points in RP1, and that Q actually represents the so-called cross ratio of 4 consecutive vertices of these polygons. Now think of the cross ratio as pretty much the unique invariant under linear fractional transformation. We are in a very, very small dimension here. But the interesting fact here is that once you're given a projective polygon, you can always lift it to the space, one more dimension, R2, with the satisfaction of one condition. And this condition, think of it as the equivalent of arc length preservation. So there is a unique lift. This is possible, I'll tell you in a second, if we consider closed polygons or polygons that close up to a monodromy, as I wrote it in a note, these are called twisted, to reflect that there is a monodromy twist at the end of your period n. If n is odd, you can always have this kind of lift from a projective polygon up to a curve in R2 that evolves, that in the moment has no evolution. But if you look at this simple flow, this is simple up to this coefficient here. If you ignore this coefficient, this evolution here is a discretization of a translation flow. This coefficient is there in order for the arc length preservation to work, in order to preserve arc length. So as such, it is called the projective tangential flow. The correspondence between this flow and this cross ratio is pretty simple. It's 1 over a product of determinants of successive, well, actually vertices of the polygon, skipping 1. And as such, we say that the Volterra model, like the NLS, is a projective realization of, or this one, sorry, the gamma flow is a projective realization of the Volterra model. Now, you can construct general polygonal evolutions. And the way you do it is very similar again to the whole scheme we have been building up. Suppose you have a lift of a projective polygon, again, a bunch of points in RPM now, go to higher dimension, with an arc length condition. Arc length is simply that the determinant of the first n+1 vertices of your curve in m plus 1 is equal to 1. Think of it as an equivalent of our Klein condition. Just like for Pinkall flow, if you shift the index by 1, and you use the fact that this Klein condition is preserved, you find that gamma n plus 1, gamma sub n plus n plus 1, it has to be a linear combination of the other vectors of your frame. And those are simply the geometric invariant. So imagine in R3, right, if you have a curve, you keep differentiating the curve, and you're going to obtain the curvature of the torsion, and past the third derivative, you get nothing new. And this is exactly what's happening in the discrete setting. Construct the moving frame using exactly these points on the curve. Advance the frame, shift it. So this is equivalent to taking one derivative and obtaining the Maurer-Cartan equations that encode the invariants. Okay, again, so far, nothing different except for the discrete setting where differentiation is replaced by a shift in the index. Vector fields, projective vector fields that are invariant under the projective group are linear combinations of elements of your frame. Coefficients, they have to be functions of the curvatures and shifts of. Write down the resulting polygonal evolution given such a vector field. That evolution induces an evolution of your moving frame, require compatibility, and the Klein preservation condition again says that the trace of your Q has to be 0, so it has to be in the algebra in a way. So again, as in the continuous case, compatibility and Klein preservation are key to integrability. Now, we picked up a paper by Gloria, Marí-Beffa, and Jinping Wang from 2013, where they wrote down one of these ODE systems for a curve in projective space, and the corresponding ODEs for the geometric invariant, so the equivalent of the curvature flows. And this is what you would see if you were interested in the standard integrable systems. And in fact, these equations, these sets of ODEs, they are pretty well known. They are known as the AGD flow or Adler-Gel'fand Dikii flow, or generalized KdV equations. They're discretizations of those flows. The generalized KdV equation was first actually written down by Lux. Then Adler-Gel'fand Dikii proved that they were integrable exactly by finding two compatible Hamiltonian structures at the level of the loop algebra. And those are well known as AGD brackets. Now, using the same kind of reduction idea on a quotient of the loop algebra by a normal loop group or loop subgroup, Gloria and Jinping showed that the ODEs for the curvature are Hamiltonians with respect to two Poisson structures. They got stuck on showing that these Poisson brackets were compatible. They're already complicated. I show you an example here for simple m equal 2. So we are in RP2. Here, the operators are written in terms of the curvatures. They're written in terms of the shift, the right shift operator, equivalent of derivative, if you wish, and this combination, which actually does play a role in a recursion formula. But once you increase the dimension of your space, they weren't able really to show that these two brackets are compatible. So there comes the geometric picture. So we lift the pictures to the level of the curve evolution. The curve evolution in Rn+1, in the n+1 dimensional space, under the action of SL n+1. So we introduced two, well, a simple form, a simple one form that is constructed out of elements of your moving frame, and as an argument as a projective vector field, which is Arlen preserving. And in terms of these two forms, we this theta form, we introduced two forms. One is the differential of theta, and the other is this expression in terms of theta and the L operator. And we proved that these two forms are actually closed, and they have non-trivial kernel. So they're not symplectic like Pinkall's, but they're so-called pre-symplectic because they have kernels. The kernels are small dimensionals. And next, what we did is that we showed that if I give you a smooth function, so I'm after Hamiltonian vector fields, even with the pre-symplectic forms, you can actually construct from a smooth function explicitly a vector field, which is the Hamiltonian vector field of F with respect to one of the two forms. If you do the same with two smooth functions, you can show that this pre-symplectic structure evaluated at these corresponding vector fields are exactly the corresponding Poisson structures of the two Hamiltonians. And moreover, the map that takes the differential of F to your XF, even if you don't have symplectic structure, is in practice the inverse with respect to the second symplectic structure on symplectic leaves. Now, what we get with all of this machinery of lifting the Poisson evolution of the curvature to the symplectic structure on the space of curves is the compatibility of the Hamiltonian structures in a couple of lines of calculations in any dimension. And the way we do it is simply through this type of identities. We need to show that the sum of the two Poisson structure found by Gloria and Jinping is a Poisson bracket. The only thing left to verify is really the Jacobi identity. That's where they couldn't do it. And once we have the correspondence between the Poisson brackets and the symplectic or pre-symplectic forms on the corresponding Hamiltonian fields with respect to omega 2, the whole calculation reduces in showing that this quantity is zero, but this is an immediate corollary of the fact that the omega 1 is a closed two form. And that's it. So a couple of comments here. The kernels of the two symplectic forms at the level of the curves are actually very interesting. The kernel of omega 1 is generated by only two vector fields. One can be thought about as a translation field. The other one is almost like as an acceleration field, as a second derivative. It's very much akin to the seat of the integrable hierarchy for Boussinesq-like systems. We can construct the Hamiltonian in terms of that one form. They're also very simple. The kernel of omega 2 is generated by simply the isotropy algebra of the monodromy. So they're really the symmetries of the monodromy. And in that sense, omega 2 can be reduced to become a true symplectic structure. Now, the point we left at is the construction of integrable hierarchy, and that will be next. So we are going to soon resume this project, and I would like to just leave you with that. All right, I thank you for the talk. And, you know, if you're interested in this kind of, geometric flows related to integrable PDEs, I have a few papers here. In particular, you know, Pinkall's paper is very pretty to read and very short. It gets you right into the spirit. And then all of the papers we in part wrote and Gloria wrote. And the latest paper with Tom Ivey, we have been looking at integrable geometric flows in yet another kind of geometry, Legendrian curves and transverse curves in the trisphere. Let me see, I have let me check if there is a, okay, that's it. Okay, thank you guys. Any question?
So thank you very much.